So we're going to look at some double integrals in polar coordinates, and I'm going to do a fairly thorough explanation of these. Usually, we're familiar with Cartesian coordinates. So that is, we've got an x-axis, for example, and a y-axis, and our point, xp, or p, is described by an x location and a corresponding y location, right here. If you make a small step in the x direction and a small step in the y direction, you end up sweeping out an area dx times dy, right? And this is your so-called infinitesimal area element in Cartesian coordinates. Polar coordinates, on the other hand, are different. You still have if you like, you can put in the Cartesian axes. You still have point P at the same point, right? Can be XP, YP in Cartesians. But what we do instead in polar coordinates is we describe by this distance r and this angle theta. The idea is that we've got a different representation of our points. We've got some radius and we've got some angle, which still specifies point P uniquely. So our coordinate pair in this case is RP theta P in polar coordinates. Let's think about how we convert from Cartesian to polars. So let's draw out my diagram again, just a lot bigger. X, Y. This is a Cartesian XP, YP. So let's draw in the radius, R. Let's draw in the rest of this triangle, XP, YP, like that. Right, so we know this distance here from the origin is XP, and we know that this distance here from the origin is YP. It's a right angle triangle, right? Or there if you like. So we can compute the radius using Pythagoras theorem. So we know that r squared equals xp squared plus yp squared. Next job is to compute this angle here. And since we know the opposite side and the adjacent side, we've got a tangent relation. So we know that tan theta p equals yp on xp. This gives us the two relations rp equals square root x squared plus y squared, and theta p equals the inverse tangent what we also have from this is a couple of relations for x and y in terms of r and theta. So if you like, this tells us what r and theta from Cartesians to polar. So if you like, this is a Cartesian to polar transform. Now, using the same trig identities, you will notice that this distance here, right, that's r sine theta. That's just trigonometry again. And this distance here is r cos theta. Okay, so we also have x in terms of r and theta, and y in terms of r and theta. right? So in general, of course, you're not dealing with a single point, you're dealing with any general x and y, and that's what lets you convert between these two things. So this is polar to Cartesians. All right, so you can relate the two coordinate systems like that. The next thing we have to worry about, especially when we come to doing integrals, is the area elements. Now, as I said for Cartesians earlier, we've got a very simple coordinate system. We've got x, this is say x plus delta x, this is point y, this is y plus delta y, right? In the limit, as these things tend to zero, right, in our integral sense, this area, this infinitesimal area dA is equal to dx times dy, where limit delta x tends to zero of delta x equals dx, right? So these things become the infinitesimals in this limit, right? In Cartesian, in polars, it's not so simple. So this is r, and this angle is theta. Let's now extend r by a distance dr. So this point is r plus dr. And now let's extend theta by an angle d theta, or delta. I should write deltas here because I'm about to take a limit. This distance is still r, by the way. So all I'm doing is rotating around by some angle delta r, or delta theta. I'll try and sketch an arc in there. So my area element isn't a rectangle anymore. It's like this sector, this difference of two circle sectors, right? I want to compute the red area. Now the red area is the difference of the yellow area minus this black area here, right? So we can compute the different areas of my circle sector, and this one here is the all-important dA. All right, so the area element when my coordinates change by a little bit. We'll call this area B, and we'll call the overall region area C. All right. The area of B, the formula for a sector of a circle, it's pi r squared times the angle in radians. So, well, times the fraction of the angle in radians, sorry. So that is, the angle is d theta radians divided by 2 pi. Right, that's the sector of a circle area formula. DC, sorry, the area of the sector of the circle C note that the angle, the d theta thing doesn't change, nor does theta ever actually feature in this, right? It's only d theta that happens to be important. Because obviously if you just rotate this around a bit more, it's going to be still have the same area. Right, so dA, which I should write delta A because it's not an infinitesimal yet, delta A equals the area of C minus the area of B. So pi r plus squared delta 2 pi minus pi r squared delta theta onto pi. Right, and this can be expressed as, right, after, or it can be simplified to r dr d theta, sorry, delta theta plus delta r squared delta theta over 2. Okay, so that's just simplifying that expression there. As delta r tends to 0 and as delta theta tends to 0, you've got these things tending to infinitesimals. This, because of the squared, disappears faster than this term, and you have that your area element in the limit is r dr d theta. So you've got a new area element dA after you neglect this squared higher order term, right? So it disappears in the limit. Your integral then proceeds pretty much as normal, right? If you have some integral of an integrand f of r theta dA over some sort of circular region, whoops, you can integrate this by putting in theta limits, r limits, f of r theta r dr d theta. Note that dA gets replaced with r dr d theta because that's our infinitesimal area limit in polar coordinates. Okay, so let's do an example to cement this home. Let's consider an example in Cartesians, and then we'll put it into polars. So consider 0 to 1, 0 square root 1 minus x squared plus y squared, dy dx. Okay, so this region, we can sketch it in Cartesians. It's a semicircle like this, right? So radius 1, this is square root 1 minus x squared. All right, so this is well described in polar coordinates. Our r would go from 0 to 1, and our theta would go from 0 to pi. So we'd have constant limits in this case. So 0 to 1, 0 to pi, r dr d theta, right? So this, remember this r goes with this here. We have to translate the integrand from x and y coordinates to r and theta coordinates. But we know how to do that. We decided that this is our transform up here. So we can either substitute x equals r cos theta, y equals r sine theta, and recall that sine squared theta plus cos squared theta equals 1. Always, that's an identity. Or we can note that x squared plus y squared is r squared. Right, so we've got x squared plus y squared. So we're going to get r squared there. So we have to do this integral r cubed over this region. So that's easy, right? So that's the integral 0 to pi of r fourth on 4 between 0 and 1 d theta, right? Because we've got 3 r's. So we've got an r cubed, add 1 to the power, divided by the new power. So that's 1/4 times pi when we do that theta integral. All right, so let's think up another example. Let's keep the region of integration the same.